no worries.
Yeah.
Okay. So let me introduce. So I mean, probably I don't need to introduce Adrian, but it's really a great pleasure to have you in our seminar. So thanks for making the time. Adrian is a faculty of radiology at Harvard Medical School. He is also a research affiliate at MIT at CSAIL, where he got his PhD from as well. So he's around for a while in the field, and I think he's an excellent example of people covering the whole spectrum of machine learning and medical image analysis. So I guess it's fair to say that you're deeply rooted in medical image analysis, and hopefully still are, but he's making contributions to the ML side as well. So he's around at NeurIPS and also computer vision, CVPR, and so on. So his work is influential in many communities now. And I think it's also fair to say that some of his like more recent work over the last couple of years has really helped to resurrect a research area that was almost dead, which is image registration, which in the past was like one of the big pillars of MICAI, and then got a little bit into oblivion, I guess. But some of his work really helped to get back this as a research topic, especially using now deep learning for this. And I assume and hope that some of your talk is covering that as well. So I guess this is all about how we can use unsupervised learning for image correspondences. So really looking forward to your talk, and the floor is yours.
Okay, all right. Thank you for that introduction. Thanks for having me. Yeah, so I am going to mostly focus on learning-based registration, and I'm going to try to highlight as much as possible sort of connections between what we do nowadays with learning stuff and sort of classical registration work, and how we can sort of learn from one and the other. So I'm going to start with a little bit of a story, which is kind of halfway through my PhD, about 5-6 years ago. When I started my PhD, I started with something like 7 images, and that was kind of like a normal data set at the time. And about halfway through my PhD, I got several thousand images from collaborators that we had to analyze. And a lot of this analysis involved aligning the images, so doing registration and trying to do some sort of spatial alignment of these images, look at disease, all kinds of spatial modeling. And so the important part here was that as part of whatever we were doing, we had to align images. And so we also were trying to do prediction, which I thought was really cool. We had these spatial diseases that we were looking at, and we wanted to combine these with other data and make interesting predictions. And so all of this involved alignment. And so at the time, there was this one problem that kind of stood in our way, which was how long everything took. And so that's kind of where all of this started for me. And to be clear, if I wanted to register 2 images at the time with the top piece of software, it would take a couple of hours, especially for the images we were dealing with. And that meant that even if you just wanted to register everything once, it would take forever. But the other thing it meant was that as a PhD student, you wanted to do interesting modeling that involved deformations of images and things like that. And you just essentially couldn't do it. Anything you came up with would take days to try on a few images. So this was, at the time, this was a really big problem. So what I'm going to talk about today is learning-based registration, that one of the effects it has is it takes this time down dramatically. And that's not only a good thing because you can run big data sets much faster and that sort of thing, but it actually enables new types of models that at least we couldn't effectively do before. And now everything's, at least for us, everything has changed. So the way this is going to go, although it kind of depends if people have questions and kind of take it a different direction, but I'm going to try to talk about some connections between classical models and the work that's been done in registration over the last few decades and neural networks, and sort of how we go from one to the other. I'll talk about results, but also about sort of extensions to these models, lessons that we have, and sort of different directions that we've started taking them. And then I'll talk about 2 or 3 recent applications, or I should say sort of new projects that came out of this that at least we've been really excited about. Okay, so I'm sort of assuming everyone is mostly familiar with registration, but just to sort of be clear, what I mean is that, so I'm referring to the formable registration throughout most of the talk. And I really just mean finding this sort of deformation field that warps one image onto another. And so it's a dense field. You get a little vector at every location that connects the 2 images. Now, the most important thing I want to start with is that there's an incredible amount of research in this. As Ben just said, there was really decades of really innovative and very nice research. And it all kind of revolved around some sort of optimization. So you were given 2 images and you had to run some optimization that would align them. And in my opinion, at least, there was a lot of research in the various aspects of this optimization. So the way this optimization worked is it said, okay, after you warp one image, the 2 images should match up in some way, and the field should be smooth in some way. And how, what the terms looked like involved a lot of research, and how you optimized everything involved a lot of research. And there's a lot of progress in this. And so I really think there's a lot that we can learn from all of that modeling. But one of the problems that's sort of inherent in this approach is that it's quite slow in the sense that you have to do a new optimization every time you see 2 images. And so you kind of learn nothing from registering 2 images. And that turns out to be a problem, because if you have to register a lot of images, well, by the time you register your 10th pair of images, you should really kind of have learned how to do it quickly. So with that intuition, we started seeing learning-based registrations come about. Now, I think the very first methods that try to look at learning were really a long time ago, and they kind of went through iterations, but they really became successful or popular when convolutional neural networks became popular. And so around, I want to say 3 years ago, we started seeing a lot of these sort of supervised registration methods come into Makai. And the idea was actually very simple. We would have a neural network in the middle that would learn in a supervised way to regress out the deformation field. What this meant is you needed pairs of images, and you needed some supervision, some ground truth deformation field. And you could get this in many ways. You could simulate it, you could run some classical algorithm, and so on. But the bottom line was you got some data set together, and then you ran some registration. And this was great, but it had some limitations, some significant limitations. There was a lot of work ahead of time to train your networks, and they were fairly limited in what they could do. And so this is where we kind of came on the scene and trying to sort of look at how do we avoid the limitation of having to treat this supervised. How do we just deal with data only? So if we only have images, how can we sort of still learn these sort of functions? And the other thing we started worrying about at the time was that everyone who seemed to be coming into this field was essentially throwing away all of that work that had been done in registration before. And they were essentially coming from a machine learning point of view and saying, well, we're just going to take all the machine learning from NeurIPS, and then we're going to apply it to a supervised setting mostly, and see what happens. And so that was a problem to us. But obviously the advantage you could have was, the immediate advantage was that you could do things really fast. And so that was a nice motivator at the time. Okay, so I'm going to talk about our sort of framework in this. And I just want to point out that in parallel to us, there's a lot of other methods that have been developed. But I'm going to talk about ours that's called voxelmorph. And at the time, so this was about 1.5 years ago, we were thinking about how do we exploit both worlds? How do we take advantage of the classical modeling that's been done, but also take advantage of the power of neural networks? And so I'm going to talk about starting from some models, probabilistic generative models in particular for diffeomorphic registration. And this is all classical stuff that we can learn from that really has provides really nice properties, topological guarantees, uncertainty estimates, and a bunch of other stuff. And then I'm going to talk about how to connect this with neural networks and the sort of properties we get from that. One of them is that they're fast, but it turns out there's all these other things that come with this sort of thing. And then I'm going to also mention a bunch of applications we've been looking at. Okay, so that's a bit of an intro. I don't know if I said it at the beginning, but please interrupt me or maybe pose questions or something. And if there's nothing else, I'm just going to kind of get going on all this modeling. So, okay, we start with a very straightforward, very simplistic way of looking at modeling image pairs. We start with one image. I'm going to call it a moving image. And I assume in my model that I warp this image with some randomly sampled warp that I'm going to talk about. I add some noise. This gives me a second image. So this is a sort of very simplistic model for how one image is warped from the other. And in particular, I have this parametrization of a deformation field. And I can borrow all kinds of different parametrizations from classical modeling. You could just have the parametrization be the field itself. So the field itself could be sampled from a distribution. Where field could be some embedding of deformation that we want to sample. And there's some work on this being done in parallel to voxelmorph. I'm going to work with stationary velocity fields. If you haven't seen stationary velocity fields, there's not sort of much that you need to know for this talk, except to say that given something called stationary velocity field, which is a dense vector field, I can get a deformation field, which is diffeomorphic, so it's invertible and has some nice properties, by simply doing something called vector integration. And luckily, we don't sort of have to learn how to do that because there's wonderful researchers before us that have sort of done this efficiently. Okay, so I have this very simplistic probabilistic model. And I'm going to add a prior to my deformation fields to essentially say that they're smooth, right? And this is, again, you can sort of borrow from classical models how to do this. But essentially, the core idea is that I want some spatial smoothness. And given this probabilistic model, I want to learn the following probability. I want to say, given two images, how do I find the probability of registration? Meaning, given two images, what's the most likely deformation between them? And maybe some probability around that. Okay. Now, depending on the specifics of your model, this can be intractable. It can be really hard to compute. And so what we're going to do is we're going to borrow a bunch of development from the variational inference literature. And we're going to approximate this distribution, this sort of true distribution, this probability of registration with some other probability. And what we want from this probability is we want it to be easy to evaluate, because the whole point we're trying to avoid here is to compute this true distribution with something easy. And then we want them to be close. Okay, so how do we achieve these properties? Well, the simplest thing we can do is we can say, well, let's just make this a Gaussian, right? And if this probability, this variational probability we're coming up with is a Gaussian, then it's really easy to evaluate. And so the way we're going to make it a Gaussian is we're going to sort of come up with this neural network that takes in two images, because the probability is conditioned on two images, and it outputs the mean and some covariance matrix of the deformation field. So to be clear, this mean is an entire field, it's a velocity field, and the covariance, which we make diagonal, is some uncertainty around that. Okay, so given two images, I sort of know the mean and the covariance of the distribution. So that makes it easy to evaluate, right? It's just a neural network. And the other thing I wanted was for these distributions to be close. So I wanted this approximating distribution to be close to the true distribution. And the way we're going to do that is we're going to minimize the KL divergence. Now, to be honest, you could do this in many ways, and there are some simpler ways than this, but this is sort of a standard way to minimize the distance between two probabilities. And the reason I like this derivation is because when you write this, mathematical statement out, you come back with some intuitive terms. Now, the way we minimize this is you essentially wiggle the network parameters until Q is close to P. Okay, so that turns out to be our loss, right? Because we're changing the network. And so we get these two terms. And I really like that these two terms actually mimic the classical models. And so what this first term is saying is, well, whatever comes out of the network should actually match my prior. And my prior, if you remember, was really just about spatial smoothness. And so if you had made the prior about something else, it would be reflected here when you're trying to optimize this. And so the second term is this sort of image matching term, right? And it's again very similar to what you had in the classical modeling. And what this term is saying is that while you should sample from your distribution some deformation, you should go from velocity field to a deformation field. You should then take this deformation field, warp one image, and make sure it looks like the second image. So this is essentially an image matching term that's very similar to the classical model, but in this optimization, we're not optimizing one deformation field. We're optimizing a neural network, which is a global entity, that somehow is able to give us good deformation fields. So, if you look at this slide, I just want to sort of highlight that I could have just avoided the last 5 minutes by just putting up this slide, right? Oh, look, we're doing a neural network. It takes down a bunch of images. It outputs a deformation field. That's the end of it. But I really want to highlight how close this sort of neural network that is unsupervised is to the sort of classical optimization that we used to do. And importantly, the difference is that we're optimizing the parameters of the neural network. And that has all kinds of repercussions, good and bad, that we have to kind of be aware of down the road. Okay, now once we've optimized this and we have a trained model, registration is really easy, right? We take in two images, we output this probability, we can sample from this probability or take the mean of the probability and get a deformation field. So that's simple, it's fast, and we get some uncertainty estimate at each voxel, which is kind of a cool effect. Now, I want to highlight that everything I just went through has a name in machine learning, which is amortized learning or amortized inference. And the idea is that we build networks that learn to approximate a standard optimization. So in a classical model, you have this loss that you optimize for every instance. This is true for registration, but it's true for a lot of things that we used to do. And now we have this neural network that approximates the output of that optimization. Okay. And so this is valid for many, many problems, and it's a growing subfield of machine learning. And at the end of the day, if you want to use this, you can just sort of use the neural network instead of your optimization. Okay, so I'm gonna go into a bunch of results and properties of these things that we've analyzed, but I wanted to see if there's any questions at this point first.
Not on the chat yet, if anyone has a question at this stage. Nope. I do have one, but it might be
okay.
a long, maybe one for later, but just on this point of the neural network parameters.
Yeah.
Now, comparing them to the traditional approach, you typically, I guess in most approaches, you would have more, I guess, let's call them interpretable parameters. Let's say you optimize control point displacements or something like this.
Yep.
So do you see, I guess you already pointed towards there could be cons in doing this. So how much do we know what we optimize for when we do it within neural network parameters versus more explicit parameterization of deformations?
Well, so I think a lot of the classical parameters and hyperparameters are still used here. You just also have to deal with the neural network. So, you know, if you had properties of the deformation field representation that you would design or learn, those can still be incorporated in these models. If you had properties of the optimization that you thought was useful, particularly in medical imaging, you can still use that in your optimization. I think in terms of parametrizations and what you're learning, you've almost strictly increased what you need to worry about, which is the neural network and how you learn those parameters and the hyperparameters of the neural network. So in that way, it's a harder task. But it turns out there's some good things that come with that. And in particular, the neural network tends to have a kind of regularizing and a robustness effect in the optimization. But I think with respect to the parameters question, I think you've basically increased your parameter world. And I will talk a little bit about how sort of hyperparameters play into this whole thing. Okay. I'm not sure if that answers it, but you can ask me.
No, there are questions coming in. Why do you need a probabilistic unit? Can the unit be used to directly regress the velocity field?
Yeah. So good question. I should have made this clear. So you don't need to output probabilities. It depends a little. Depends a little bit on the model that you have here. So for a very, very general model, you need to sort of a very general probabilistic model. You need to do variational inference because sometimes you need to learn how to go from this to this, or from whatever your presentation is to your neural network. To your deformation. And so if you want to do that and you want to keep your probabilistic properties, it turns out variational inference is one of the really good ways to do it. But to answer the question directly, if all you care about is the best estimate for deformations, and maybe all you care about is the deformation or the velocity field, then indeed you don't need the sort of uncertainty part. I agree. But I just wanted to highlight that when you start with the probabilistic model, you can get an estimate of that probability from your neural network. And that probability can help you down the road. It can give you uncertainty measures. It can lead to robustness. It can give you interpretability, and so on. It's the usual sort of things that you get from a probabilistic model. So the answer is you don't have to, but this is sort of what comes out.
Okay, great. I think you also answered the follow-up question that was from Miguel. I believe so, Miguel, right? Otherwise, say if this wasn't the case. Yes, okay. Thank you.
Okay, so I think I'll move on. Okay, so just briefly going to mention some results before I kind of go into some analysis of them. Well, originally, so again, this was about 1.5 years ago, or maybe 2 years ago, we started, the first thing we did was, well, these are neural networks, and we're going to throw a ton of data at them and see if they work. And they did work. But I just want to highlight that the results I'm showing you had a lot of training data. And this was all MRI, brain MRI, just because I work a lot with brain MRI. And the very first thing we wanted to do was to look at runtime. So as I mentioned, a lot of our analysis was using ants. Ants can take maybe somewhere between half an hour to a couple hours on a single CPU, single thread. Now, to be clear, you can get this down to half an hour, but it has all kinds of repercussions in terms of accuracy and properties of your field and so on. Now, there are a bunch of other tools out there that have since then made a lot of progress on runtime. NiftyReg can take a few minutes. If you tune it to do really well on our data, it takes maybe 10, 20 minutes, but it's still a lot slower than we would like. And Voxelmorph, because it doesn't need to iterate once you've trained it, it takes less than a minute. Now, the exact amount it takes depends on how many features you have and that sort of thing. But the very first attempts we had were somewhere between 30 seconds to 51 seconds, which is the model I'm showing. And then if you have a GPU, well, then it takes less than a second. And this is all for 3D large, several million voxel images. Okay, so runtime seems to be a good deal. But does this actually work? Well, how do we know if registration works? It's a challenging question. And so the easy way to do that is to outline a bunch of structures on your images, or maybe annotate, and on both of your images that you're registering, and then say, okay, well, once I register this image onto this image, I hope the anatomy matches. So we do this, take this image, warp it, and then we see, oh, look, they sort of match, at least visually they match. This is with voxelmorph, this is with ants. Okay, but we should look at this quantitatively, right? And so quantitatively, higher is better on this graph. And I have a bunch of different structures, and the main sort of takeaway is that voxelmorph was doing very much the same as the baseline, despite the fact that it was 3 orders of magnitude faster or something. Okay, so this was encouraging at the time. It was also encouraging that voxelmorph was actually diffeomorphic. So this is the number of voxels that sort of didn't fold onto itself, onto themselves. Now the baseline here is ants, but again, this is one of these issues where a lot of the classical methods are diffeomorphic, but you have to run them with certain settings and or run them long enough or something like that. And so we would find that with the default stuff in ants, you would get a few voxels that were not diffeomorphic. So maybe 5,000. Now this is very few because there's 8 million voxels in an image. But we were very happy that depending on the settings, again, voxelmorph would have very, very few, maybe 10 or 1 or something like that. So at least there was very good potential that voxelmorph would be very fully diffeomorphic. And as I mentioned, you can also get measures of uncertainty or variance at different locations. Now, we didn't really go into this analysis too much, but it was really nice to see that you would get images of uncertainty, and you could sort of tell where your deformation field is or isn't sure. And obviously that depended a lot on the contrast you had. Okay, so this was sort of the initial stuff we looked at, but then we started getting these questions both from a more technical side and from a utility side. And the very first question that came all the time was, well, how much data do you really need? And this is because, in practice, a lot of people don't have thousands of images to train on, but also it's an interesting question in terms of learning, because intuitively, once you've seen 10 images registered, you really should know what you're doing. And so we did this very, very simple analysis where we trained a bunch of different models with 10 training images, 25, 50, 100, registered to an atlas. Now, this is no bells and whistles, no data augmentation, nothing like that. And what we found was that after having even 10 or 25 images, it got pretty close to the state of the art on a separate test set. And then once you got 50 or 100 images, you were basically there. So you certainly didn't need 7,000 images. But the other thing we thought of was, well, wait, if voxelmorph gets you pretty close, couldn't we just take the result of voxelmorph and do some classical optimization? And we did that in the sense that we took the result of voxelmorph and just optimized the deformation field on the GPU for a few seconds. I think it was somewhere between 15 and 20 seconds. And that got the results to the state of the art. And so this is telling you that these learning-based methods, first of all, learn from very little data and without any tricks. And then on top of that, they are able to, if you're unhappy with the result when you have very little data, they're still able to give you a very, very good initialization. Okay. Now, so a little bit about hyperparameters and parameters in general, just going back to Ben's question. One of the hyperparameters, there's really one really important classical hyperparameter in this whole thing, which is the balance between the two terms, right? Between the image matching term and the regularization term. And you can, the really nice thing with classical models and probabilistic models is you can initialize these or sort of think of the right one based on the meaning that they have in your probabilistic model, which usually have to do with sort of noise in your data or expected deformations. And so we initialize this to some value somewhere in this range, and we found that, oh, already the results are pretty good. We then sort of moved around there, and we found that it's pretty robust, but you can get the optimal value here as opposed to here. But the really interesting thing to me was that if you turn this off, the results dropped by a few dice, but it wasn't they didn't drop dramatically. And we sort of started wondering, well, why is this? The results were actually, visually, they were still pretty good. In classical models, you can get some really, really bad behavior if you turn off the regularization. So we're trying to understand why. And it turns out neural networks have this kind of regularizing effect. You have this one global network that's in charge of everything, all these data. And so they have this sort of regularization effect. They're not completely free to do whatever they want within one image. And so that was kind of a nice result, something to be aware of. Also, just a very quick answer, sort of statement. At the very beginning, we only had very small GPUs, and so the most features we could kind of fit was somewhere between 16 and 32. But it turns out if you have a lot more features, the networks can do better and better. And so now we have these 24 or 48 gig GPUs, and we can build bigger models, and you really get an improvement in dice. And so you can go beyond the classical models. Now, I talked a little bit about segmentation. Segmentation is, we were using segmentation as a way to evaluate data, but then we thought, well, if we have some segmentation, why can't we use it in training? And so we had these models where you would use your segmentations as part of the loss function. And so what that meant was you would say, well, I don't just want my model to warp one image onto the other, but if I have segmentations for that image, I would like the segments to match up after the deformations. And so this kind of underneath it all, when we poked at the network, it turned out that this taught the network to essentially extract features that had to do with segmentations, because it would sort of learn that segmentations are important. So it would be forced to learn a little more about anatomy and try to match up anatomy. And so that's really nice, because then at test time, you don't actually need segmentations. You just plug in two images, but the registration turns out to improve dramatically in terms of aligning structure. Again, well beyond the state of the art. Okay, so that was just a whirlwind of a few quick analyses we did. I want to go into, in the time I have left, 25 minutes, I want to go into sort of two other problems, but maybe I'll take a second to take some questions here.
Yeah, any questions from the audience? Can I just ask, the segmentations you incorporate during training, are they containing the structures on which you later compute the dice? Because I assume yes.
No, yes and no. So we did analysis of kind of holding out different amounts, doing things like having a training or having only sort of white matter, gray matter, and CSF, but then testing on all the subcortical structures. And the sort of quick answer is that anything helps. So like if I have just white matter, gray matter, CSF segmentation, and then I test on all the other ones, like all the small structures, they get a boost as well. Even if I only have, say, hippocampus segmentation, and then I test on hippocampus, but I test on a bunch of other stuff as well, those get a boost as well. So essentially, almost anything we tested, there was some boost to having some segmentation.
Yeah, okay. And a follow-up question, did you look at validating the uncertainty estimates?
We did not, and really it's just a matter of not having enough time. it's a prioritizing which projects we cared about. But I really think that there's a lot to be done in there. We just haven't had the manpower.
Okay, and then one more. How many atlases did you use? I assume this refers to the point.
This was all. So in the results, it was all one atlas. I mean, we just sort of worked with one atlas that we created.
Okay.
Yeah. Unless this was a question on how many segmentation maps did we use at training, in which case I forget, but we've done tests with as few as five images that were segmented. Okay, so I'm actually gonna, let me see. I'm gonna skip the very first application just because the other two I think are more exciting, but I wanted to sort of make one point. So I'm gonna skip just a couple of slides here, but there's one point that I really liked, which was that neural networks seem to have a very interesting property of being a lot more robust to local minima. In a lot of the classical methods would kind of get stuck with data that didn't have the sort of nice properties. If it was very sparse or very noisy or something like that. And so I worked in my PhD for years to optimize classical methods, both ANDs and some discrete optimization methods actually. And eventually after optimizing them to death, they did decently on some really, really difficult data. And then out of the box, Voxelmorph did just as well. And what was happening is that the networks don't get stuck as easily, because if they see some image where they would get stuck locally, the next iteration, because of the stochastic nature of the training, they will see some other image and they will continue to learn. And so we noticed this behavior quite a lot, that although they would be given the same difficult images to train on, they would get stuck a lot less than classical methods. And so that's a sort of a nice property I wanted to mention. And in particular, we deployed this on actual clinical data that came from sort of really difficult stroke data set, and it did very well. Okay, but the two sort of projects I wanted to mention. So template construction was just from a utilitarian point of view, we had this question from a lot of people sort of, well, I have a bunch of data, I want to register to an atlas, but I don't have an atlas. What do I do? And then it turned out to lead to some interesting learning-based concepts. And so classically, the way you build a template or an atlas was essentially you started with some representation of it, and then you would register a bunch of images to that representation, and then update your representation, for example, by taking averages, and then register again, update, register again, update. And this was at least the predominant method that I knew at the time. And this took a long time, but and so we thought, oh well, we could replace the registrations with Voxelmorph, and that would help. But then we thought, well, actually, what we're learning here is a global representation. A neural network is this global entity that in some way represents your data. It sort of learns from the data that you give it. And so if while you're training, you are already learning some global entity, why not also learn the template? And so we can also start again from a probabilistic model and all that, but from a learning perspective, all that I'm doing here is I'm taking this Voxelmorph sort of structure, and I'm changing one of the images to be a learned atlas. In other words, what I'm telling the network is, don't just learn the convolutional filters, but at every location, tell me what is the most likely voxel intensity that I can register all my images to, right? And so I essentially, I'm just changing this, and then I tell the network to learn everything again. And what comes out of this is a network that can register your data, but also an atlas. And so this was the atlas that we got on these T1 brain images. And it's a little smooth, but it's actually very nice. It's got a lot of the properties that we want. And it's a global representation. You essentially get this for free while training Voxelmorph. There's nothing that you don't have to readapt your framework in some crazy way. And so we thought, going back to this whole thing I said at the beginning about how it's not just about making these as tools, but also they enable all kinds of modeling that was really hard to do before. Well, one of the things that was really hard to do before with templates was that if you had a really large population, a very heterogeneous population, so let's say, simplistically speaking, you just had patients who were from 20 years old to 90 years old, having one template is really not a great representation for that. And so what people would often do is they would break down by age groups, and they would have several templates, let's say. So you would have maybe 3 templates or 5 templates. And that could help you in analysis, although there was also arguments against that. Now, we thought, well, this discretization isn't very useful, or sort of it has a harsh aspect to it. And so we thought, why don't we, since it's so easy to model templates now, why don't we model a template as a function of an attribute that we care about, for example, age. So in other words, we changed the network a little more, where we say, you know what, don't learn a template. Instead, learn a function that gives me a template as a function of an attribute. So for example, if I give the brain of a 45-year-old, I would put in the age 45 here, and the network would have to give me a good representation of a 45-year-old brain. And I could also try other attributes, you know, gender, genetics, and that sort of thing. And again, this is a very slight modification. It's a slight modification to the probabilistic model. It's a slight modification to the sort of voxelmorph architecture. And these are the sort of the age templates that you get. Now, to be clear, I'm just showing you 7 templates here for different ages. So this is a very sort of young brain. This is elder brain template. Now, I can really show you a continuous movie of this. I don't know how well this shows over Zoom, but I'm going to play it a couple more times. So you can see how the ventricles are growing over time. You can see the rest of the brain shrinking. So again, I'm going to play it again with age, right? And so the neat thing is that I don't have to estimate only, you know, 3 templates if I have a really large population, but in fact, I can sort of learn templates as a function of a bunch of different attributes. And so this leads, I'm not going to sort of go into detailed analysis here, but this leads to all kinds of improvements. Like, for example, you can, if you build segmentation maps with these templates, then it can lead to significantly better registration, because you have, for every patient that you get, you have a template that is a lot closer to that patient. You can also extract interesting patterns. So for example, for the atlas I just showed you, the ventricles, you can measure how fast the ventricles grow and how fast the hippocampi or other structures atrophy. These are, to be clear, we never modeled this. We never put this into the model. We never said, oh, you know, we know that these properties happen. Instead, the model just sort of learned it, which I think is very cool, because it opens up sort of the possibility that you can learn all kinds of high dimensional patterns as a function of sort of really interesting attributes. Age is an obvious one, but we're looking very actively into genetics right now. And you can apply this to all kinds of things. One of the most interesting things I think that we're applying it to nowadays is pediatric data. These are essentially infants that were just born, some of them prematurely, and we're building atlases for them from really young ages, so 20 days and some younger, to a couple of years old. And the really interesting thing is that because they're growing through these, sort of developmental stages in the brain, the same MRI protocol actually shows very different contrasts, especially for the very young ages. This has to do with sort of myelination of the brain, but you can see how the white matter actually flips in contrast, which again is something that, well, we know from neurobiology, but it's really interesting that the sort of approach can just pick it up. Okay. So I sort of breezed through that, but it's sort of an active area of research for us. We had a machine learning sort of paper on that, and we're trying to apply it to all kinds of data sets, and every data set we apply it, we learn something new. So I think it's a really exciting area. But I wanted to save 10 minutes for this really recent work on modality agnostic registration, and it's both incredibly recent and just a little bit bonkers to me on what sort of the networks are able to do. And so there's been a thing that's been bothering me for a long time with these networks, which is probably the biggest negative of these networks, which is that they only work on whatever they're trained on. Meaning that if I train them on a bunch of T1 images, and let's say they're T1 clean MRI images, I really don't expect them to work on other stuff without retraining. And the problem with that, of course, is that it makes their scope very narrow, right? I would really love to train some network on something and then just be able to deploy it on, T1 or T2 or CT, or even just T1s, but with different processing, with the skull, without the skull, that sort of thing. So how do we avoid this dependency on training data? And the very first thing that comes to mind, I think, when you say that is, well, we're going to use some sort of data augmentation, right? We take the data we have, and then we are going to modify it, change it, flip it, all kinds of things. And we did some work on that. But we've recently been thinking, well, what if we just go crazy? What if we just synthesize images that sort of even maybe make no sense, but they try to teach the network something? And so we started doing this in a segmentation network that I'm not going to go into details, but I'm going to just have a slide on the sort of synthesis process. And then I'll come back to sort of how we use this in registration. And I think Benjamin, who's the first author on the segmentation work, gave a talk in your group recently, so I'm not going to spend too much time on it. But I want to sort of highlight the idea of synthesizing images beyond what you expect. So we assume for a second that we start from some input label, some segmentation map of images, of brains. So it looks something like this. And then we're going to synthesize, or we're going to deform these label maps to just give us some variability of structure. And then inside every element there, we're going to synthesize some intensity. We're just going to fill in every structure with some intensity. We're going to add some noise. Then we're going to add some sort of effects, some blurring, some bias field, various things like that. And then we get sort of our final image. So starting from some input label, we synthesize some image. Now, this image that we're synthesizing is very much a T1-like image, but we can start doing crazy things, right? We can start synthesizing images that really don't make any sense. You would never see them. So why would we do this? Well, what we were thinking is that by showing the network really crazy contrasts, it will learn to essentially be independent of contrast. It will sort of learn that the exact contrast doesn't matter. It doesn't tell me too much. What I need to learn is something about how to extract structure. And so we did this for a segmentation network, and these are sort of papers at Middle and Mikaitis here, but I want to transfer that to registration. And so the simplest thing you can do is you can start with a brain segmentation, and then you synthesize two different brains, two different segmentations from that by just warping. And then you synthesize two different brains. Now, again, the brains are really crazy, right? You would never see a contrast that has the white matter dark on one side and bright on the other, but we're giving these two images to the network, to a registration network, a voxomorph-like network, and we're telling the network, well, give me a deformation field that makes sense. How do I know if it makes sense? I'll talk about that in a second, but essentially I'm giving the network really crazy contrasts. And the hope, again, is that the network learns to somehow not get fixated on the exact contrast, but instead learns to sort of just match up features that make sense. Now, I'm doing this with brains, and at some point we thought, well, wait a minute, why do we need brains? That concept I just described has nothing to do with brains. It's about matching shapes. And so we just came up with this sort of way to create shapes. You can do this in many ways. And so they just look like this. Right? Just come up with a bunch of shapes. Then you warp these two shape images. So you get essentially the same shapes that are warps of each other. Fill in a bunch of random intensities in there, add some effects, some noise, some bias fields and stuff like that. And now we're going to use these images to train networks, which is even crazier, right? But again, it's going to teach the network something about contrast invariance and shape invariance. So we start from these segmentations. we generate the images, we feed these to the neural network, and we get some deformation out. Now, we want the deformation to be smooth. We always want that, or somehow regularized. But the interesting question is, how do we know if it's a good deformation? Well, we could use some sort of classical sort of multimodal metric like normalized mutual information. But what we've found is what we thought was, well, wait a minute, we have these segmentations that started the whole game. Why don't we make sure that whatever the network does can lead to a good alignment of labels? So remember, the network never sees the labels, right? Because that way we're able to deploy this network to any image, but it has to align the labels. Okay, now how does this work? It's a bit crazy. Well, let's sort of quickly look. We did a bunch of classical models, and safety reg deeds. We tried other ones. These are sort of the best ones that we could get to work. And we first tested it on just T1 to T1 real data registration. Classical models do well. The voxelmorph models, we trained some voxelmorph models on real data. Now these are bigger voxelmorph models than before, so they do a little better than the classical methods, but they're trained on real data. And then these blue ones are the models that are trained on completely synthetic data. They never see real data. Okay, so the one that's trained completely on shapes does as well as classical methods. Not quite as well as the voxelmorph trained methods, but as well as classical methods, which by itself is already pretty crazy because it's never seen a brain image. It's never even seen the shape of a brain image. And then the one that's trained on brain-like images, but again, never a real image, does basically as well as voxelmorph. So that's already like a pretty encouraging result. But remember, we didn't want to test this on T1 to T1 data. These are just two variants of sort of T1 to T1 data sets. And we never really wanted to do that. We wanted to look at how well does it work, across modalities or with modalities it's never seen. And what happens there is the voxelmorph methods, well, they crash. So for example, when registering T1 to PD, the voxelmorph methods, they're like, well, I've never seen this, so I'm not really going to be able to do well on this. But these other methods, these sort of voxelmorph based on shapes and synthesized images, they actually do as well as classical methods or better, which again is pretty crazy because they've never seen real data. And so we've essentially eliminated this need for data training. And this is consistent across basically every test we've done. And so I want to just very quickly look at what is going on here. Why is this working? Well, we sort of set up these four images, four image pairs that are the same two subjects, but the first subject was essentially scanned with, well, we took some raw data and we simulated different scan types. So, from PD to T1, but it's the same subjects, okay? And then we look at what voxelmorph, the features that come out of voxelmorph. And we find that these are the features of the last layer of voxelmorph. And we find that the features depend on the input contrast, meaning the feature for this contrast and the feature for this contrast look different. As you can see, these two features, which have different contrast as input, look different. So obviously the network depends on the contrast that is inputted. The new networks do not have this property. Despite the fact that I'm giving it different contrast, the network at the last layer has the same feature over and over, which essentially means it has learned to be completely independent of the exact contrast that is given to it. Which we thought was really, really cool. Essentially, these networks are, by being exposed to so much, have learned to sort of ignore the exact intensity. Okay, so before I sort of do a summary slide, I just wanted to mention that all of this work has involved a crazy amount of people in the last 2 years. It's been fantastic to work with all these people across a bunch of different institutions, MIT, MGH, Harvard Medical School, even UCL in London, and Cornell. So it's been great. And so as a quick summary, I mostly talked about voxelmorph and all kind of derivative analysis or work that we've done. And I didn't get to cover everything I wanted, but we started from these classical models, really. We just borrowed from these giants that did all this wonderful work. And then we turned into solving those models with neural networks. And that gives us all kinds of nice properties. Some of the nice properties that we had before, but also fast registration, some built-in regularization, some built-in properties, although some limitations as well. And then, we looked at all these interesting, I think, areas of limited data, segmentation, learning templates, synthesis, and then there's all kinds of other things that you can do with these networks. So that's it. Thank you.
Thank you so much, Adrian. I'll do the applause for everyone. You got a lot of compliments already on the chat. People saying this is super clear talk, and they are thanking you already halfway through.
Great.
So brilliant work. So I have a couple of questions lined up.
Sure.
So let's go with them. So Cheng is asking, so is in the modality agnostic work where you do these synthetic samples, do you require a reasonable deformation model between so to generate the source target?
Yeah, so so the answer is kind of. So what we originally said, what we originally found was that the answer was yes, meaning we have to have somewhat reasonable, you can't be just insanely crazy, but it didn't matter how reasonable. So if you were, like if you varied it by a factor of 2 or 3 or 4, how much you warp these, like the maximum amount that you would warp them, it would make a difference of a half a dice, but it wouldn't completely crash your network. So that was our original observation. But actually, there's a bit of a balance. It turns out you can go you can go crazier and crazier, but then you need to have bigger and bigger networks. So if you have really large networks, like 256 features at every layer and a bunch of layers, which for registration is a really big network, you need 24 gigs at least to train it. It turns out you can go quite crazy with your simulations. And I think this has to do with the fact that the network learns to respond well to even crazy deformations. And in that span, it learns to deal with the real stuff as well. And by the way, sorry, while I'm talking about that, let me just make one quick mention. We had a very early version of this that I actually sent to Ben on archive after we did about a month of work or something on this. But all these results are actually new. Like we've noticed that essentially the summary is, if you have larger networks, you can go even crazier with your simulation, and your networks will do better than everything we've seen, better than classical methods, and in many cases better than voxelmorph. And so we're due for an update of archives.
Great, very interesting. So there's another question on, I think also the synthesis part, the Perlin noise model that you use. So the question is related on whether this still somewhat resembles, I guess, like cortical folds or things you do see in the brain. So do you think the same type of synthesis model would apply to other anatomy?
Yeah, so we're actively, I had a slide on this, but I think I hit it. But so to be clear, I think I didn't talk about the Perlin noise. Someone must have read the paper or something. But to be clear, the way we simulate these shapes is by essentially just coming up with a bunch of noise images, and then we take the label that has the highest noise. We did not at all simulate anything that had to do with cortical folds or something like that. The only thing we tuned in that process was to make sure we have structures that are both small and large. So both structures that are maybe a few hundred voxels altogether, to structures that are tens of thousands altogether. That's the only thing we tuned. So we didn't really tune, to sort of simulate the folds or anything like that. Having said all that, to be honest, we haven't tested this on like liver images or something like that. We've been mostly working on brains. And to be honest, part of the reason that's true is because there's all these interesting properties that we can test still on brains, and that's the data we have easily available. I really do suspect it would work well on at least MR of other data. And then once we go beyond that, I mean, if you're trying to register ultrasound, I don't know, but you know, I suspect it can be extended to that. But yeah, so nothing specific to brains, but we also haven't tested much outside.
Okay, great. There's one follow-up question from earlier, which I don't completely understand. So Joaquin, you might have to chip in there. So the question is, for the Atlas registration task, do you think we can solve that using random deformations only? So we essentially don't need the training inter-subject pairs.
I'm not fully sure I understand either. We don't do any so sorry, that's not true.
Do you want to clarify maybe?
Yeah, sorry. I anticipated that I probably need to clarify that. Thanks, Adrian, for this great talk. So what my question was essentially, so if you think about the domain agnostic part of the work, where you have intensity variations and random deformations, we generate the data. But you find out that the model works pretty well against data in terms of intensity variation, but also any deformation. So my question was, do you think going back to the one domain situation, do you think do we only need to train, so if we only train with random transformations instead of using these inter-subject pairs, do you think that would work?
I see. So let me be clear about something. Although we have used voxelmorph and presented results on subject-to-subject registration, none of what I talked today requires it. Let me just be clear on that. So all of the registrations, all the Atlas building, all of that was built on subject to Atlas registration. But your question is different, which is, could we just simulate, if I understand correctly, could we just sort of randomly deform, like take one Atlas and then randomly deform it a bunch and then teach the network to register back, if I understand correctly, right? And so the answer is, that would do okay, but not as well. I mean, we did it, we tried it. And so the problem there is you're not exposing the network to, while you're exposing it to good deformations, potentially, you're not exposing it to the sort of variability in image texture and image contrast that you would get even within a T1, right? Or maybe some subjects have different number of folds, for example, and that you're not exposing it to that either. And so that, like, it turns out you need data somehow to show it that variability. So it's not just the shape variability, which really the original models kind of did in that supervised setting, but also you need exposure to variability in anatomy that manifests in slightly different way, right? Different texture, for example. And so you need that. So now you could do that with, you know, you start with 10 or 15 different images and then you synthesize data from that and you kind of mix them up and stuff. So, you know, in that whole line of work, you can definitely combine simulation with real data. And that can get you pretty far. Honestly, I suspect that with just about 5 real images, you can train one of these models to sort of be as complete as possible. But you do need some data.
Great. There are no more questions in the queue, and I think we have taken a little bit more time from you than we said. I just wanted to thank you again for a brilliant talk. I think it was really excellent. People enjoyed it.
Thank you.
The compliments are coming in on the chat. Thanks so much for joining us. I'm sure you're happy to follow up on anyone who wants to ask further questions or something.
Yeah, absolutely. And thank you so much for having me. This was great.
No,
really appreciate it.
Thanks so much. Take care.
Bye, everybody.
Bye-bye.